this isn't going to work. You're going to see my answers. Oh, that's what I should have done. You guys are just getting all this extra seconds. I know, you're already winning. I'm looking for my remote. That's okay.
Wait, do you have to do number 8?
No.
Okay, wait, I'm done.
Okay, stand.
What? Peter? Hey, you're blocking me.
I'm done? Oh my gosh!
Chill. Like, God.
You like throw yourself out the window. I'm done.
You were the first one. Hey.
That's so funny. All right. Let me see, Justin.
Oh, dear.
Oh, so funny.
You know what?
Is it good?
Justin's good.
Turn it.
Justin, check the rest who are standing. At least he and I agree, so maybe.
Yeah, the words for this.
So we were supposed to write the questions. That's writing all the questions. Me too. Yeah. It like bothers me if I don't write the questions. Yeah, I have to write the questions. I can't like just write the answers. I know how to do this. No, Issa, you can't.
Hold on. So Justin.
Let me just open the front and explain.
That's not the order.
Oh no, already? All right.
Oh, you subtract.
Go sit. If Justin needs to already explain. Let me just go ahead and unfreeze the screen. Justin, you're the teacher. Ready, set? Why is A what it is? Go.
Okay, so
Oh, I just didn't get 12.
A is 0. Did everybody get that?
You're a terrible teacher.
Oh, she ready?
Yeah, but he's answering questions on it. So, go, Justin, teach. Number 1 is the whole thing, Issa.
2, like 3, 0, like the bounds are the same, like 0.
Wow. His mind.
Okay, stop. Be serious.
From 1 to 5 of g of x, and you're looking for like the
Additivity.
So that's enough. Anybody?
Because you'd have to switch it, so you have to switch. So you knew it was negative.
The way I think of it is like a line. So like 1, it's like 1 is 6. I can go from -4 to 6. Like, yeah. So that area right there is what's
Okay, Justin, just show the additive. What is it? Just subtract it.
Didn't you get it wrong?
I figured it out though. That's the thing. Because I realized what I did. And I think that's the
Justin,
Okay,
just show
hold on. Let him do his explanation. Hold on. Let him give the explanation.
And then to 5, all of it is 6, right?
Oh, I get it. Never mind, Justin.
Yeah, show brackets. That's good.
So
Okay,
it's -4 plus x equals 6.
Or 6 minus. Okay, Aryan, how would you explain it?
I just said that if you're taking the whole from 1 to 5, you're given the 1 to 5 and you want to know from 2 to 5, so you just subtract the piece that's not included.
But that's technically what Justin is thinking as far as whole minus. Maggie, how would you explain it?
additivity product of the additivity.
Okay, go show it on the board.
I don't know what to tell you. That's a lot of thought.
I just wouldn't have.
So pause. Listen to Aryan's words for Justin's explanation real quick. So Aryan, say yours one more time.
Okay, so if you're given the whole, which is from 1 to 5,
Mm-hmm.
you're trying to find the piece from 2 to 5, you just subtract the piece that isn't included. So you take the whole thing and subtract the piece from 1 to 2, because that's not included.
So Justin was very visual and thinking about like an actual number line progression. Aryan is like, oh, it's the whole thing minus a part will give you the leftover. And then Maggie's trying to show the additivity property.
You just put them together somehow.
I mean, that's one way, Riley. Pause. Does Maggie's work too? To go from 2 to 1 and 1 to 5, but the 2 to 1, she has to flip the bounds, hence the negative. Yeah, that works too. The additivity. That's actually how I think about it, though. But I thought about it that way, like, oh, to get to 2 to 5, oh, wait, we have to go, and then we have to go backwards. So I did both of them all together. But that's okay. I would have done both all together. Okay, hold on. Hold on. Did you guys have any other questions? Because his and my answers checked. I didn't say they were perfect. I mean, I think I got him right, and I think he got him right. But do you have anything else that you have discrepancies on? All right, what did we not get to do was number 8. I don't think we necessarily need to do it. Can we just walk through how we would do it? Is that okay? You think that's fine? Yeah? I know, they are. I was kind of like, nah.
She said well.
With food, if food is a little more brown than normal, has nothing to do with people's race. It's well done. There you go. So it probably was in the fryer a little bit long. But here's the funny thing. I was wondering why my boxes were really heavy today. I was like, oh, they put a lot in. And I'm like, oh, they gave me the whole batch because it was a little brown. Anyway, that's okay. They're sweet. Well, we got more donuts, right?
Do you get discounts?
No, but they're randomly nice. I think they do give me a little bit of a discount, but not a lot. I actually think they raised the price because of me. But that's okay. That's okay.
Every one day in the year. I don't think you do. Wait, do they know your order? Like, do they just?
I just text the owner and I'm like, hey, can I have my 10 dozen tomorrow? And he's like, sure. And I go in, I'm like, hey, John. He's another guy. I'm like, thanks, John. See you next week.
How much do they charge you for each donut?
I don't know. It's $22 for 10 dozen. So that would be like 2.2 per dozen, right? So that'd be less than 20 cents each.
Oh, because the place right here.
Yeah, they take cash only, and they got mad at me the first few years because I would come, and anyway, so I just don't go to them anymore. But they do have nice donut holes. They're just like the tight ones, and some people like them, and yeah. And they're not like the nice warm because they have them ready early, which is cool because they're super efficient. Christ Bible, the church, Mr. Carmichael's church, they get donuts from down there. So I've mended the relationship, but I have my guy on, and I prepare, and I can pay credit card. It's just all good things. Okay, now that we recorded that, hi donut holes. Question, what's going on here? It's not telling us to solve it. It's telling us to find a range of it. MVT? Sure. How? MVT says that there exists a perfect rectangle that equals. You would need to know what the equals was to do MVT. Kind of, but we'd still have to. But we'd have to know how to solve it. I would do IVT. If there is a perfect rectangle, there's a perfect rectangle. There's a perfect rectangle that equals that integral. How could we say there's an in-between? Kathy, what are you thinking?
I was just thinking that like the bounds of 0 and 1 could be used in some way.
Maybe. Could the bounds of 0 and 1 be used in some way? What's this function do? Strictly? So if I thought about what was going on at 0, and if I thought about what was going on at 1, what would the actual area have to be? Isn't the perfect rectangle going to have to be in between the lowest possible rectangle and the highest possible rectangle? Didn't we write notes on this about a minimum and then a maximum area? So what would be the area of the minimum using 0? Well, the base would be 1, right? But what would the height be? Because don't we just plug into our y equals? Yeah. So plugging in 0, wouldn't that be 0 and the square root of 8? Ah, we do want to plug in 1, just not yet. We're going to plug in the upper bound, right? So the upper bound also a base of 1, but what's my height going to be this time?
3.
Oh, so what's the actual area going to be in between? 2 root 2 and 3? Oh. Why? Because of IVT. And because of the nature of square root of x plus 8, the minimum value is at, the maximum value is at. So there's a minimum rectangle, minimum area, and a maximum area. It's going to be somewhere in between. Is that a pretty stinking good approximation? So if you were to solve this and if you were to get a decimal, couldn't you see whether or not you were correct if it fell within that range? Anyway, let's go back to section 6.4, fundamental theorem of calculus. We talked about that guy yesterday. The antiderivative part, how to define an antiderivative using, oh, that's cool. So wait, is FTC part 2, is it really just a definition of an antiderivative? Maybe it's not a definition of an antiderivative. Yeah, this is one we already read yesterday. But the one we take the derivative of the accumulator function, take the derivative of the antiderivative and get back to the original. It's the antiderivative part because, in a sense, you're deriving the antiderivative. The original function, if you want to think about like what we saw yesterday with the AP guys, the original function would be that you had been given something that defined the antiderivative. And then for some reason you were needing to take the derivative of that function. So that has to do with our ddx from a to x, but we also talked about how going from a to u is something where we have to just kind of reorient our brains. But I think we're well on our way. The second part of FTC is where we ended yesterday. As far as the evaluation piece, how to practically apply FTC. We're not going to go through how MVT and IVT ends up proving this infinite sum really just comes back to f of b minus f of a, even though that is pretty cool, but we saw that last year. But I want you guys with me really quickly just to antiderive and plug in bounds. Should be easy, right? Shouldn't make mistakes, true? So let's go. All together, let's just go. What's the antiderivative of x to the 3 halves? Because remember we add 2 over 2, and then what goes in front? And what are we doing it in between? Which one do we plug in first? So we have 5 to the 5 halves minus 0 to the 5 halves. If we were trying to make it match, long answer, we box it, we're done. We're smart, we're BC. I should say we're experienced. But how would you simplify this if you needed to? Yeah. Not with a 2/5, but with the 1/5, yeah. So this is really 5 to the... So we could change this into a square root right now, or we could try to simplify this power of 5 with that power of 5, right? What happens if you're doing like bases division? What do you do to the exponents? So it's 5 halves minus 2 halves would be 3 halves, right? And 3 halves is the square root of 5 cubed. Isn't that the same thing as? Could you get there? What's another way of thinking about this besides the square root of 5 cubed? How about 5 to the 1 and a half? Anyway, all good things. Could you get there? That's the question. Wouldn't it have been messy if you had to do this? Like, would any of you have gotten the 5 to the 5th and been like, 5 times 5 times 5 times 5? Right? Wouldn't it be easier if we could, before going there, if we could simplify anything out? And then sometimes it's easier, instead of thinking about it as an improper fraction, to think about it as a mixed number, 5 to the 1 1/2. Anyway, final answer, 10 root 5. 2 times 5 to the 1 times 5 to the 1/2. All right, cool kids. What should we think about here? And why am I rewriting it? He was meaning the bounds, and the bounds aren't upside down, it's lower to higher.
2x then -2, and just add 1, so
Yeah, I think that's a smart idea.
x. Yeah, there you go.
I didn't change the bounds, I rewrote the inside function. Yeah. And then it'd be -1, so I just made it -2 over x, and then who do we plug in first again? Mm-hmm.
2 minus 1.
Okay, some people have already started homework because they're like, psh, we got this. Do you have this? Psh, yeah. But are there still places to make mistakes? We know in long answer that we stick it to the man, and to some extent you're okay, but to some extent if you stick it to the man too early, are you making yourselves practice making it match? Just beware, because when do a lot of mistakes occur? When you're going fast. Some of you guys realized that today, made some mistakes. Maybe it was because it was a lapse of understanding, but a lot of you, maybe it was because you just didn't spend enough time thinking on it. When you're going fast, or when there's a lot of computational work to be done. Just be careful. A lot of these would be just simple make it match ones. Okay? I know, but I like how they word it. Wait, we already read this. No, we didn't. We read it for the other part of FTC. This is for the f of b minus f of a part. At the risk of repeating ourselves, it's difficult to overestimate the power of the simple equation. It says that any definite integral of any continuous function f can be calculated without taking limits, without taking Riemann sums. I lost it. And often without effort. What? Not sure I agree with that. So long as an antiderivative of f can be found. Okay, it's a little bit better. If you can imagine what it was like before this theorem and before computing machines, aka calculators, when approximations by tedious sums were the only alternative for solving many real-world problems. What? They had to use Riemann sums because this wasn't around? Struggle. You can imagine what a miracle calculus was thought to be. If any equation deserves to be called the fundamental theorem of calculus. It's surely the second one, except last year we called it the first one. Whatever. We don't care, right? FTC is FTC, and there are 2 parts to it. Are we all in agreement? Cool. We already know all these? Have we already been using this one quite a lot? Why can n not equal -1? Because you would try to do the rule and it would be over 0, which is undefined. Wait a minute. X to the -1 is the same thing as, and who's the antiderivative of 1 over x? ln of absolute value of u. Hey, are the integrals of sine and cosine confusing? Only if you have issues with the signs. Be careful, right? The signs. The S-I-G-N-S, but very good question because I thought of it and I was going to spell it and I was like, forget it. But Aryan still got me. Why is the integral of sine a negative cosine? No. Oh, yeah, it is. Because the derivative of a cosine is a negative sign. We have to train our brains to be ready to go backwards or forwards. A lot of you guys eventually got there last year, but just a few of you, it's still like a hole. Or we're out of practice, so be careful. Ooh, what's total area? What's total area? I would say if you see the phrase total area, a better way of thinking about it is area between, but all the area between. Total area, if it is area between, will be like total distance traveled, should always be positive. So, not sure if you're ready to answer this yet. If you get a negative, one of 2 things happened. Any ideas? If you're doing area between, total area, if you get a negative, what could have happened? Maybe you did it wrong. There's a mistake. No, like in the solving, right? Like maybe you set it up correctly, and then you solved, something went wrong in between. Or what could have happened way back at the very beginning? What would make it negative? Well, that's true. I guess it could be 3. Your bounds could be off with the correct integrand, correct solving. Your bounds could be right with the correct integrand with wrong solving, or your integrand could have been switched. It could be another mistake. I mean, I just added one.
Like, don't you always do a positive rate even if it's like negative on the graph? If it's like 5, you do. If it's like down there, 5, you say 5.
If you're doing total distance traveled, yeah. So if you're given a graph, maybe you assign the wrong signs to it. But if you're actually solving by hand, you probably won't be able to visualize whether it's above or below. Does that make sense? The first one was bounds wrong, which messes up everything. Second one was the work was wrong, which messes up everything. And then the third one was the integrand to begin with was switched. Meaning, what if you do a lower minus a higher instead of a higher minus a lower? Wait a minute, what allows us to not stress about higher minus lower, lower minus higher, right, left, top, bottom? Absolute value is our fail-safe. Wait, how do we integrate with absolute value then? And that's going to account for what Riley was saying, some above, some below. We need to split it up because they're going to behave differently. Some will stay the same, and some will need to switch. So that's where we're going. That's where we're headed. What's this example? Find the total area between the curve and the x-axis. Oh, this is such a nice problem because what do they give you? Bounds. Well, they give, okay. It's nice they give us an equation, otherwise. Second of all, they also give us bounds, because if they don't give us bounds, do you remember what we need to be considering? Zeros, maybe domain, intersections is usually, because if it's between, we try to think about intersections. Okay, whatever, they give us the bounds. Do we just go for it? Do we just say, oh, sweet, negative 2 to 2 of 3x squared minus 3, let's go. Is that a smart idea? No, because you have no idea what you're doing. Like as far, that sounded bad. Visually, you have not considered the cost of just throwing it in and going, oh, there's a life lesson in that. Coming back, consider the cost. It was in my Devo yesterday, Hebrews 11. Everybody who walked by faith, there was a cost. Coming back. It was a good one. Although the Devo app is called She Reads Truth. There is one called He's Reads Truth, and it's on the same Hebrews 11. It's just going to be different. Pause. Kiddos, am I good to go or not? Who can give me a defense as to yes or as to no?
Well, no. There's probably.
Yeah, part of this.
It is both, right?
Where are my zeros? So 2 and negative 2, uh-oh. Looks like this, right? Because my intercepts, sorry, I just did my x-intercepts real quickly, are going to happen at 1 and negative 1. And my bounds are negative 2 and 2, so I'm going to have some below and some above. Why is it bad if I just integrate right now? That's going to be what kind of value? Positive. That's going to be what kind of value? Positive. Those are going to be, it's not going to do total distance. It's going to say, oh, forwards and backwards and backwards and forwards. And you're going to end up somewhere accounting for the changes in position. I don't care about that. I want how much, how much, how much, all positive. So what do? Now pause. Mathematically, without a picture, how could we have figured this out? Which would have made us consider the zeros. Because what happens at zeros of an absolute value? Wait, piecewise, piecewise function. Absolute value, what do we have to split up the pieces with? The zeros. You're welcome, it's back. Well, nothing else, you'll have absolute value mastered by the end of BC. Well, by the time we get to sequences in series, and then maybe everything else will fly away. But coming back. Absolute value, well, we've done piecewise. Guys, just consider it. We've done piecewise functions this year quite a bit. And when we make the piecewise, what do we consider? Well, on one side of 0, it stays the same. On the other side of 0, it needs to flip, right? We don't need to consider all that right now. All we need to consider is zeros are important. Yeah, they are. Okay, cool. When are the zeros? Hey, is this symmetric at all? So couldn't we just technically go from 0 to 2 and then just double it? What do you want to do? Do you want to do this piece, that piece, that piece, or do you want to do here and here and double? Okay, so let's go ahead and change this just to be double of going from 0 to 1 and 1 to 2. Does that make sense? I apologize. I hadn't totally finished yet. Technically, this is going to have absolute value. This is going to have absolute value. And then these are going to have parentheses. I was building up. Okay, the absolute value of 3x squared minus 3 dx. 3x squared minus 3. True? And why are the absolute values now outside the integral? Why was that legal? Because I split it up, it meaning the region up at the only possible place where there could be a switch in orientation. Now guys, you don't need me from here, so I'm just going to integrate. Cool? You integrate, me integrate. We'll integrate together. On the inside is saying, hey, I don't know who this guy is, so if he ever goes negative, he has to flip up because of total distance area between. And we cannot pull outside until we split up at the zeros. Right. The problem is when you integrate, the problem isn't the integration, because the antiderivative is going to be the same no matter what for all the pieces. The problem is, how do we consider this with those? Does that make sense? And if we don't split it up at all, and we take the absolute value after we plug in, the subtraction already occurred. See what I mean? If you put it in your calculator, you're great. It's going to do all the work for you. The problem is the by hand. Sorry. I think integrals of absolute values are. What do we get? Negative 2 is an absolute value, so positive 2, and then we have 2 minus negative 2 before an absolute value is still a positive 4, and then we end up with that times 2, which is going to end up being 12. Anyone beat me? Oh, because I was being lazy and didn't want to split it up into 3 pieces, because I would have had to do negative 2, negative 1, negative 1, 0, 0. Well, actually, we could have done negative 1 to 1, and then 1 to 2. I just said, it's symmetric. Can we just do that doubled? So I started at 0 instead of negative 2. Yeah. But without knowing symmetry, would that have been wise? No, that would have been awful. But I knew the symmetry, so I went for it. You guys can start considering the next one, because we still want to find the total area between. Uh-oh. We still want to find the total area between. Uh-oh. But first of all, anyone match up number 12? Sorry, the answer of 12? I'm going to be nice. I'm not going to have you solve this by hand, but can you guys set up an integral expression that would solve for what we need? What would you guys say? Cool. What do we got? Because a little bit of area here, a little bit of area there, all the area. Any worries about absolute value? Nope. So let's pretend it's one of those AP ones that says just express it as an integral. We're done. Okay. I know, me too, right? Whoa. Once I start getting some FRQs on the tests. So I want you guys to set up what you would need to do in order to be able to solve by hand. Ready, set, go. You yourself and you. Do you know what you would need to do in order to solve by hand? You can set up an integral expression. I don't mind. No, just set up the integral expression. When you apply it, like it's not already there. It depends on whether you know the upper bound, lower bound. If you do know the upper bound, lower bound, there's no need for absolute value as long as you orient it correctly, or the right bound, left bound, if it's in terms of y. But if you're not totally sure, or if you're not totally sure, like you might know the general picture, but you're not sure which one's which on which side, what I'm thinking of right now is implicitly defined functions where you'd have to like find the original and then reflect it, and then like that starts to get really messy. It's probably easier to throw absolute values in, but splitting them up at the intersections splits it up at the zeros, so there's no extra work really involved besides piece by piece, make sure it's positive. Does that make sense? So, let's see how you guys did. Hopefully. True? Does anybody have a guess as to where most people make mistakes in solving with absolute value? Actually, no. But good guess. Keep going. No?
Oh. They forget to take out the absolute value from the x minus 2 and use the parentheses.
Kind of. It has to do with the actual solving. Like, if it's stuck in here, wouldn't everybody kind of get lost? I mean, I guess they could just leave it in there. Most kids that know what to do with absolute, I mean, there's the ones who don't know what to do. That's a whole other category. But the ones who know, where do they make mistakes? Usually they know the zeros. Usually they know the split up. Usually they know, okay, absolute value this, absolute value that. Where do they make mistakes? When it comes to f of b minus f of a, they think that every single piece needs to be positive instead of doing the subtraction first and then putting the absolute value. That's where all the mistakes of someone who understands what to do almost always occur. So just a quick reminder, I didn't make you guys keep going, but if I had, you would have had 1/2 x squared minus 2 from negative 1 to 2. So in a way, Maggie, I said yes because the problem is from here to here. The absolute values they usually know are on the outside, but as soon as they go here, they forget, PEMDAS says do what's inside first before applying the outside. So when they go to plug in the 2 and they're like super focused, like yay, 2 squared is 4, and then minus, and then 2 is 2, and then when they go to this, then they do the minus, and then they plug in the negative 1. Now this one's kind of awkward because not much really changes. But what a lot of people do is, okay, you have to be positive, and you have to be positive, and you have to, no. The whole thing, once you're done, yes, I know, I haven't done the rest. The whole thing, once you're done, needs to be made a positive. Does that make sense, guys? So that ends up being, oh, hey, 2 minus 2 is 0, minus 1 minus 2 is a negative 1. Well, I guess this one isn't quite as fun. But if they did something, no, this one's going to end up being the same. But if you were to have something like 4, yeah. You could, if you had something like a 4 right here, 4 minus, if you made that a positive 1, it's going to be very different than 4 minus a negative 1, right? So whatever's in here, you have to do it first. It does end up being just 1 plus. You have to keep going. But the most common mistake is here. ironically, if you know what you're doing. Do FTC first, do f of b minus f of a first, get a value first, then absolute value it at the end. Does that make sense? One half of, oh, because I'm silly and can't do math. I was doing like a, I don't even know what I was doing. It's going to be negative 3 halves, right? 1 half minus 4 halves. Oh, I just need to change that. Don't apply till the very, 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 very end of each piece. You guys ready? On your marks. Get set. Well, that's no fun. Can I not fit the whole thing? Okay. Go. H of x is an accumulator. H of x is an accumulator. Do you now know how to work with them? Well, I would say H is the accumulator. H is... We'll slowly start playing. Already, huh? Yeah. What I would do at the very beginning of this is be like h of x is the area under f, right? H prime of x. Derivative of the integral from a to x is just going to be f of x. So the y values, right, of f, and h double prime is going to be what? Go one more. Which is going to be the... That's what I always do whenever they give me an accumulator. That way I can orient myself. They're not asking for the number. They're just asking for the sign. Yeah. Why?
Because the area of the curve is
But you don't have to give number values. You can say the integral from 0 to 6 is going to be higher than the integral from 6 to 12. Now, could we actually do some like upper and lower sums and probably talk through a little bit of that? Yeah, we probably could. But it would take, because they don't give you enough information to use numeric evidence. Does that make sense? Or numerical evidence? Guys, are we okay? This is the end. Try homework. Come tomorrow with questions if you get stuck on anything. And then we'll go over the answers to this puppy.